Let's do some transformations of tangent and cotangent curves. A lot of this should look familiar to you guys from the last section of the text. Here, I have the standard form of a tangent function and the standard form of a cotangent function. Y equals a times the tangent of b times the quantity x minus c plus d, and y equals a times the cotangent of b times the quantity x minus c plus d. In these equations, x and y, those are our variables, and a, b, c, and d are going to be the constants that determine our particular function. So let's talk about each one of those constants and how they are going to impact our parent function. A. A, as hopefully you guys remember, is our vertical stretch and shrink. A affects the vertical scaling of the function. If the absolute value of a is less than 1, there is a vertical shrink. If the absolute value of a is greater than 1, there is a vertical stretch. If a is negative, there is a reflection in the x-axis. Notice we don't call this amplitude with tangent and cotangent functions, right? It's not called amplitude. Amplitude refers to a wave height. And because we're not actually dealing with waves with these functions, we just go back to what we learned in chapter 1.7, our vertical stretches and shrinks. B. B influences the period, right? Those are our horizontal stretches and shrinks, our horizontal scaling. B affects the period of the function. Period refers to how long it takes for the function to repeat itself. And if b is negative, there is a reflection in the y-axis. To calculate the period for tangent and cotangent functions, period is equal to pi divided by b. Now notice, this is different from our sine and cosine functions. Our sine and cosine functions was 2 pi divided by b. For tangent and cotangent functions, we take pi and divide by b. The reason being, pi is the period of our parent functions, tangent and cotangent. C. Well, C is still our horizontal shifts, and the parent function will be shifted horizontally c units. And for all trigonometric functions, this is known as a phase shift. So same name as before. If we identify c, the constant c tells us how we are shifting horizontally. And d, finally, is our vertical shift. The parent function will be shifted vertically d units. If d is positive, we're going to move up. If d is negative, we are going to move down. So here are your guidelines for sketching tangent and cotangent curves. Notice they're going to look very similar to your guidelines for sketching sine and cosine. Determine the period, phase shift, and any other transformations from the parent function. I'm going to ask you specifically to identify all of those transformations. Make sure you understand them. Note that tangent and cotangent do not have amplitude, right? Again, amplitude refers to a wave height. We don't have a wave height here. 2. Begin with the shape of the parent function, include at least 2 full periods. Apply vertical stretches and shrinks. Labels to the y-axis are not going to be as necessary as the exact values may not be known. However, it's important to understand how these transformations affect the graph. In other words, your vertical stretches and shrinks, in terms of your sketches, I'm not looking for them to be perfect. Okay? 4. Apply horizontal stretches and shrinks. Those are your changes to your period. Label the x-axis to match the period. It is helpful to use half period increments in your scale, all right? Half period increments when we're dealing with tangent and cotangent. With sine and cosine, it was good to have quarter period increments because then you would have, you'd split each period into a quarter of pi. Well, in this case, because the period of tangent and cotangent is pi, each split's still going to be a quarter of pi. So we split the period in half. 5, reflect the graph over the x-axis and or y-axis as necessary. And 6, apply the phase shift and or vertical shift. And at the end of the day, if you forget all of these directions, this is what you need to follow. We scale first, then we reflect, and then we shift. Determine the period, phase shift, and any other transformations from the parent function. Sketch the graph, include at least 2 full periods, identify the domain and range of the function. Okay, So here's our standard form. Y equals a times the tangent of bx minus c plus d. Notice that if there is a period change from b and a phase shift from c occurring, that we always want to factor out that constant multiple b from both terms. In this case, I have no c value, so I don't have to worry about doing that. We'll come back to another problem where you see that factorization occur. Okay. Anyway, back to our period. How do we calculate period? Well, for tangent and cotangent, we take pi and divide by the b constant. In this case, the b constant is 1/2. Dividing by 1/2 is the same as multiplying by 2, and so our new period is 2 pi. Notice that we have given our graph a horizontal stretch. We are increasing the period. Next, determine the phase shift. Well, the phase shift is determined by the constant c. In this case, c is equal to 0. Therefore, we have no phase shift. And other transformations from our parent function. Well, let's start off with this negative in front. Notice that the a constant is negative. If a is negative, that gives us a reflection in the x-axis. Now, we also have a 2 in front of here. That 2, that gives us a vertical stretch. That is a vertical stretch by a factor of 2. All of our y values are going to get multiplied by 2. And we have a -1 tacked on to the end. -1 is our d constant. Therefore, we have a vertical shift down 1 unit. So here's the parent function, right? That's y equals the tangent of x. Remember, scale, reflect, and shift. All right? So we get rid of all of the labels on our x and y axis, and now we can begin to relabel them. Always scale first. So let's start off with our vertical scaling, because that's from A. We have a vertical stretch. All of our y values, are going to get pulled away from the x-axis. Here's what our vertical stretch is going to do. All right, all those y values get pulled away from the x-axis. Look at that one more time. Okay, all right, there is our vertical stretch. As I said, I'm not looking to see that you have a perfectly to scale vertical stretch on your sketches. As long as you can tell me that there is a vertical stretch, you're going to be in good shape. Okay, there, we did our vertical scaling. Now let's do our horizontal scaling. Let's change our x-axis labels so that it matches our period. We know that this function has a period of 2 pi. Well, how long does it take to repeat itself? I've got a midline crossing here. Here's my next midline crossing. That's going to be 1 full period. Therefore, I can label this as 2 pi. And if I go the opposite direction, because the period is 2 pi, label that guy -2 pi, which means each one of my tick marks here is going to represent a unit of pi. Okay. All right, we did our vertical scaling. We did our horizontal scaling. Next, we want to reflect. We have a reflection in the x-axis. Now take that graph and reflect it over the x-axis. That means our graphs are going to go up and down in opposite directions. Okay, we reflected it over the x-axis. And finally, we want to do our shifts. There is no phase shift. That would be from our constant c. C is 0. We have a vertical shift down 1 unit. All right, and remember that vertical shifts shift the entire graph. And so that's going to change the midline of our graph. Notice our midline here is at y equals 0. Well, that midline is going to shift down to y equals -1. All right, boom. All those points on our graph shift down 1 unit. Notice that originally it crossed through the origin 0, 1. Now I have the ordered pair 0, -1. Okay, so there we have the shape of our graph, and it might be helpful for you guys to draw in your vertical asymptotes as well. All right, notice our vertical asymptotes, that's where our function is undefined. Okay, why is that helpful? Well, now we need to write the domain. Remember, when we go to write domain, our domain is going to be all real numbers except pick a vertical asymptote. In this case, I would pick pi. That's our first positive vertical asymptote. Except x cannot equal pi plus n times however frequently they occur. Notice that all of these vertical asymptotes are spaced out by 2 pi. Therefore, our domain, all real numbers except x cannot equal pi, plus n times 2 pi. Our range, all real numbers, negative infinity to positive infinity. All right, let's try a cotangent one here. Determine the period, phase shift, and any other transformations from the parent function. Sketch the graph, include at least 2 full periods. Identify the domain and the range of the function. Okay, in this case, we have a phase shift occurring and a period change. Anytime those are occurring at the same time, we want to make sure that we are factoring out our b constant from each term inside of our trig function. In this case, I need to factor out a pi from each term inside of these parentheses. How do I do that? Well, I just divide each one of them by pi and put the pi in front. This gives me 1/2 times the cotangent of pi, parentheses, x plus 1/2. Notice, how did I get x? I took pi x, divided it by pi. Pi over pi gives me 1. This becomes a 1 in front. I have pi over 2. I am dividing out a pi. Pi over 2 divided by pi, that's 1/2. And notice that if you were to multiply or distribute this back in, you would end up with pi x plus pi over 2. Exact same function. Okay. So again, do that anytime you have a period change and a phase shift occurring at the same time. Got to do it. Okay. Let's look at our period. How do we calculate the period for a cotangent function? Period is equal to pi divided by b. Our b constant is a pi. Pi over pi is 1. All right, so this is going to repeat itself every 1 unit. Again, nice to work with these integer periods. Our phase shift. The phase shift is equal to c. Notice that the standard form has x minus c. If I get a plus 1/2, that means that my c value must be negative 1/2. I have a phase shift of 1/2 units to the left. All right, and other transformations, well, our a constant in front, that's our vertical scaling, and because it is between 0 and 1, right, the absolute value of a is between 0 and 1, that means it's going to be a vertical shrink. Okay, we have a vertical shrink. And that's everything for our transformations. So we start with the graph of the parent function. And then we need to scale it, reflect it, and shift it. All right, so we clear out all of our labels on our axes. We still have the exact same graph. And notice we have tick marks every half period. So let's scale vertically, right? We're starting with A. We have a vertical shrink. That's going to pull all of the y values closer to the x-axis. Boom. There's our vertical shrink. Again, does your sketch have to perfectly demonstrate that vertical shrink? No. As long as you make sure you tell me that there is a vertical shrink occurring, you'll be in good shape. Okay, now let's do our horizontal scaling. That's going to change our period. Well, period for tangent and cotangent, we go from one vertical asymptote to the next vertical asymptote. So I've got a vertical asymptote here. It repeats itself here. That means I can label this x-coordinate as being 1. Going the opposite direction, here I would have -1, which means that each one of these tick marks is going to represent a half. All right, vertical scaling done. Horizontal scaling done. Reflections. No reflections to worry about. Our last step is to do any shifts. And here we have a phase shift or a horizontal shift of 1/2 unit to the left. All right, so all of these points on our graph are going to move to the left 1 unit. So notice this vertical asymptote that was at x equals 0, that's going to move to x equals -1/2. This x-intercept that was at x equals 1/2, that's going to move to x equals 0. Every single one of these points is going to shift to the left 1/2 unit. All right, and there we have our final graph. Notice we can fill in our vertical asymptotes as we see here. Okay, let's now talk about the domain of this function. Our domain, as we said, is going to be all real numbers, comma, except x cannot equal, we pick a vertical asymptote. I would pick this one here at x equals 1/2 plus n times how frequently they occur. Well, notice I have a vertical asymptote every 1 unit. So that would be plus n times 1, and n times 1 is just n. There is our domain, all real numbers. X cannot equal 1/2 plus n. That will represent every single one of these vertical asymptotes, right? We would have an infinite number because they would continue as we move to the left and to the right. And our range, as is for every single cotangent and tangent function, all real numbers. All right, tangent, cotangent. Coming up next, secant and cosecant.